Hey guys, David the Physics Tutor over at GCC, and in this video this is part 2 of the mesh current analysis where we do a shortcut and just jump to our final set of equations. So I still recommend you watch part 1 so you can understand what it is that the mesh current analysis is doing. It's kind of part 2 where we can kind of just use it to get to our final answer. So again, what does step 1 tell us to do? Step 1 tells us to draw a loop and assume a direction of current. So I'm going to assume I1 goes this way. If I assume clockwise for one loop, I'm just going to assume clockwise for the rest of my loops. And then it's just like someone pointed out last time, we have current going this way, current going that way, so we technically don't know how we get there. And since I addressed that in video 1, I would highly recommend you just watch it in video 1. Because we know that I3 plus I2 is going to be equal to I1. Unless you assume different directions, you're going to have a different equation. So there's that problem addressed. And now, what does step 2 of the mesh current method tell us to do? Well, it tells us to analyze each loop individually. But here, this is where I don't have to be that little electron and follow my path. I can kind of just jump to my final set because I know that in I1, I'm going to add up all the resistor values and that's going to be the coefficient. So what do I mean by that? I mean, the two resistors are highlighted, so I'm going to do 3 plus 4, and that's going to become a 7I1. And then I ask myself, okay, I did all the resistor values. Are there any resistors that are being shared with another current? And R2 is, right? R2 is being shared with I2. And since I2 is going in the opposite direction, it should have the opposite sign. So I know this should be a negative 4I2, right? And now all the resistors are done and taken care of. So I ask myself, okay, are there any constant values? And the answer is yes, right? Because down here, when I'm following my path, you still have to follow your path. You can't just assume you're going any which direction. If I'm following this path that I set out here, I hit the negative first. And if I have a negative on the left-hand side and I want to move it to the right-hand side, I should have a positive 6, right? It's because I'm moving to the other side of the equal sign. And there's loop 1 analyzed. And what do we notice? We notice that we have the same equation here that we got here. And you might be saying, well, David, that only saved us one line of work. But what happens if you have multiple loops and multiple shared resistors, and now there's just a whole bunch of like terms and computation things that you have to take care of? Being able to just jump to that final set of equations is going to save you a lot of hassle, especially if you're on a timed test. So there's I1. Now let's do I2. I2, and again, if you think you can do it, I encourage you to pause the video right now and see if you can do it. I'm going to do it in 3, 2, 1. Okay, so step 1, again, what we do is we just add up all the resistors in I2, right? So 4 plus 4 is 8, and that's going to be the leading coefficient on I2. And notice how I'm writing these in a linear fashion where I have I2 over I2 and I1 over I1, and that's because I know I'm going to be doing some linear algebra at the end of the day, so I want to have all my variables set up. So there we go. I added up all the resistors in my loop. Now I say, okay, are there any shared resistors? And I notice that R2 is being shared, right? R2 is being shared with I1. And since I1 is going the opposite direction, it should have the opposite sign. So it should be a minus 4I1. And now we took care of every single resistor. So now I ask myself, okay, are there any constant values? Are there any batteries in my loop? And the answer is yes, because I go here and I hit the positive first. Right, and if I have a positive on the left-hand side of my equal sign and I want to move it to the right-hand side, I should have the opposite sign. So now I have a minus 2. So what do we notice there? I have the same exact thing that I got down here. So again, it's just a little shortcut into solving these equations. And so now we're at our final set. Now there's no more physics going on. The rest is just math. Now we just have two equations, two unknowns, and we're going to solve for them. But I'm going to show you how to use your calculator to do it in case you have much bigger loops and more confusing ones. So here I have my trusty dusty calculator, and I'm going to show you how to incorporate these two equations into it. And the reality is you can actually do this for any class, where if you have a system of equations, if you have two equations, two unknowns, and so forth. But let's get into it. So here, my RAM's cleared, so it's using a fresh calculator. I need to go to matrix. So I can press second, matrix, and this is going to be how I use any matrix. This is where I do all the math with any of my matrices. This is where I can actually input values into my matrices. So here I'm going to edit A, and again I have 2 unknowns, so I have 2 rows and I have 3 columns. So it's very important that you do line these up consistently. So 2 by 3, 2 rows, 3 columns, and now I'm going to enter each coefficient into this matrix because I can't put variables in there. So I'm going to have a 7, then a -4, 7, enter, enter, -4, and so I'm going to pause the video since it's very slow. I think you get the idea of how to input values. Okay, so I have all the values inputted into my matrices. Or my matrix, I'm sorry. Notice how this is the first row of values. So 7, -4, 6, 7, -4, 6. So then you just follow the leader on that, right? It's just you follow that same pattern for all the rest of your equations. Now I can go to quit. And what I need to do is I need to do some math with my matrices. So now I go to second matrix and I want to do math. And the function that I'm looking for is called row reduce epsilon form. So it's usually at the very bottom. And this is what it's going to look like, rref. This is a linear algebra function. You can certainly Google it. Again, row reduce epsilon form. And I think Khan Academy has some very good videos, but since I'm your physics tutor, I'm just showing you how to use your calculator to get you to the final answer. The row reduce epsilon form, and I need to do this function on second matrix A. And that's it. And then I press enter and I get 101, 101.25. And what does that mean? Well, remember, I1 was our first column. So this has a 1 in that first column. So that's saying I1 is equal to 1. And now it's saying 0, 1. And I2 was our second column. So it's saying I2 is equal to 0.25. And notice how that's what we got last time, right? Notice how we got I1 to be 1 and I2 to be 0.25. So we got the same exact thing, but here I didn't actually have to do any algebra. I let my calculator do it for me. So let me pause the video and write that down. So all I did here was input those values into OneNote. Now I'm going to use those 2 values to find I3, right? So we have our I3 equation up there. I'm going to rearrange I3 so that I3 becomes I3 is equal to I1 minus I2. Right, and this is going to be equal to 1 minus 0.25. Then we get I3 is equal to 0.75. And notice how these are the same exact answers that we got last time with a lot less work. I'm going to make a part 2b where I show you how you can incorporate your junction equation into there. That way you're not wondering, that way you don't have to do this final step, but if you have too many junction equations, it's just easier to do them as 2 separate things and just solve the junctions by hand. And then you just have to remember how to incorporate your answer, right? How to analyze it. And again, I do that in a long way. So if you want to see how I know which ones go to which resistors, by all means, go watch the long method. And then that's it. That's it for the mesh current analysis. I'm going to show you a second example. And here, I would like for you to try this on your own. So if you could, just pause the video, see if you can do this. I have the solution over here, which I'm going to pop up in just a few seconds. So again, pause it, try it, and 3, 2, 1, here's the solution. So this is what your final answer should look like, and kind of this is what your equation should look like. So there you go. I'm going to do a very hard example in a part 3. That way you can see what it looked like on a much more confusing circuit. All right, good luck. Thanks.